Hello friends, we are now studying limitations to classical mechanics and introduction to quantum mechanics. Introduction to quantum mechanics requires limitation of classical mechanics we have seen earlier. In this video, my motive is to recap and remove some misconception. Some of you have asked me questions, so I thought instead of having new concept, first we have to clear all the previous concept, so there should not be any mistake, there should not be any misconception. So that's why we will recap and clear all the doubts and questions in these concepts. So first of all, we have studied wave particle duality. In this, wave and particle are two aspects or nature of light. Okay, so we can either call wave aspect or wave nature. Similarly, particle aspect and particle nature. So we have seen this. So why this required? So in 19th century, in 1850 and so, Michelson showed that the interference of light takes place, and that's why light is a wave. And the debate between Newton and Huygens, which was whether the light is wave or particle, was stopped for a while. But when in the late 19th century and earlier 20th century, these two effects, photoelectric effect and black body radiation, were discovered, which could not explain by wave theory. Yeah, so we have discussed this much. We have also discussed how photoelectric effect has been taken place. We have also stated that black body radiation cannot be explained using wave theory, how the classical curve goes of intensity versus the wavelength. So if we plot this graph, so in this x-axis we have wavelength, that is lambda, and in this axis we have intensity of light, right? So according to classical theory, or that is called Rayleigh-Jean's law, so the classically it should move upwards, but what happened is it showed some deviation. So this deviation were unable to explain by classical theory, or we can say by wave theory of light. Then we will have some Planck's law. So basically, what is black body radiation? So black body radiation is any hot body. Suppose this is a hot body. So first of all, we have to define what is hot body, and actually it is black body. So we will discuss what is black body later, but let's think about black body, hot body first. So we can call this body is hot if the surrounding has a lower temperature than this body. This is very simple, so everyone knows. So black body means if this body is hot, then it will emit all the radiation in all directions. So black body will appear black because it will also absorb all the radiation when it is cold. So if it is hot, it will emit all the radiation. If it is cold, then it will absorb all the radiation, and that's why it will appear black. So black body radiation means the black body is radiating the light, but that is not why it is called black. It is called black because it absorbs all the light when it is cold. So that is why it is called black body. So perfectly black body doesn't exist, you know that, and we can achieve up to 99%. That all stuff you know. So what was the question in this? In photoelectric effect, we know that there is some threshold frequency. We have already studied that. So we state that photoelectric effect can only be explained using particle nature of light, but frequency we use in wave aspect or wave nature of light. So how we can say that photoelectric effect is only explained by particle nature? So to answer this, we need to go to the timeline of the discoveries of these effects and the theories put forward. So first of all, Planck gave the quantum hypothesis in this year. Okay. So what he suggested was the energy of the light is related with some constant which we call as Planck constant to honor this great scientist. He given this h number, but we call Planck constant, and frequency of the light. Okay, so what this is relating, so you might have studied that there are some particle characters and there are some wave characters. This energy is in fact particle character and frequency is wave character. So what Planck has done, he has interrelated the particle aspect and the wave aspect, or particle nature and the wave nature. So this concept was already established in 1900, and on basis of this Planck has explained black body radiation, why black body radiation is taking place. Okay, we have studied that is called ultraviolet catastrophe. Ultraviolet. So the same graph we have seen earlier. So this was the experimental curve, this was the classical curve, and Planck could explain, he cannot explain the perfect curve, but he can explain some little deviation, but it was still matching. There was a very small difference, so we can say that Planck's theory was close to the perfect results, but obviously this is better than the classical Rayleigh's law. Even if in black body radiation, what it suggests, why particle nature can explain the black body radiation, because as we have already discussed this concept also, that frequency is related to intensity, or energy is related to intensity in the wave theory. So as we have increasing frequency, or if we have decreasing wavelength, then what should happen ideally, the intensity should keep increasing, but that is not happening. So when we go to particle nature, the intensity is depend on only number of particles. So we can say that number of particles of this energy is higher, or this energy is higher. So here is the number of electrons or number of photons in of this intensity or this energy. That's why intensity is high at this number of particles or at this intensity. And then after this explanation in this 1900 year, after 5 years, Einstein has published a photoelectric effect in 1905. So he used the concept of Planck that particle and wave nature can be interrelated, and that's why he have used that threshold frequency. Even if we don't use the term threshold frequency, we can use threshold energy. So what basically is in the photoelectric effect is, suppose this is metal surface, so there should be a minimum energy falling on the metal surface so that photoelectron can get some kinetic energy. What Einstein used is E equal to Ek, let's say Ek plus W. I will tell what I am writing here. So here W is the minimum energy, we call it as a work function for that particular metal which is required. So light should have this much minimum energy to eject the electron, and then this remaining energy will be gone to the electron. So if E is greater than W, then remaining energy will go to the electron, and that will convert to the kinetic energy Ek of the electron. Here we don't need any frequency term, but what Einstein has used, he has used W is equal to H into F, that is H into threshold frequency. We call that threshold frequency. So actually we don't need to explain this threshold frequency term, we can just use threshold energy and that's it. But why we have used the threshold frequency term is because it is easy to measure. Frequency of light can be measured easily, so that's why we use that term. But we don't need to use the term of threshold frequency, so we don't need wave character to explain the photoelectric effect. That's why we call that photoelectric effect can only be explained using particle nature. So why particle nature is used, we have already discussed. We know all the photoelectric effect, but that was the question. If there is a we are using the frequency term which is only related to the wave character of the light and not particle. So as I discussed, the reason is we don't actually need, but we use this concept because it was already established, it was already proposed by Planck that wave and particle can be interchangeable, or we can say light is a wave as well as particle. So he actually used Planck's theory. This led to very well-known equations which was discovered by Einstein. Obviously first one is photoelectric effect, for which he got Nobel Prize, and another one which was E equal to mc square. So we call it most famous equation of the century, or even we can call it most famous equation of the millennium, which led to nuclear energy and nuclear physics developments. So Planck and Einstein's this theory and Planck's hypothesis was led to quantum mechanics as well as nuclear physics. So basically nuclear physics will come under quantum mechanics also, but still we can study nuclear physics, nuclear energy with this equation, which is a fundamental equation for nuclear energy. So this was the misconception that we are using the frequency term, so we should use wave theory, but we don't need actually to explain photoelectric effect, but we can use it because we now agree that wave and particle nature are simultaneously present in the light. So there is also confusion in simultaneous, but we will talk on that on some further videos. So the next effect is Compton effect, which was explained using particle nature of light in 1923. So what was the Compton effect? Suppose there is an electron inside the metal or inside some material, and if some certain amount of energy in form of light has fallen on it and it hits the electron, then what we observe is we get another light but with longer wavelength. Okay, and we also get some recoil electron similar to photoelectron. So there is some light fallen on electron and it gets kinetic energy. But in photoelectric effect, what happened was it was ejected from the metal surface and there was no emission of light. Here what happened is the electron has not taken outside the metal surface, it is just getting some energy, kinetic energy, and it is moving, and the light is not disappeared, it is not completely absorbed by the electron, but wavelength is increased means energy is decreased. So some amount of energy is taken by the electron and some amount of energy is remaining, which comes out as a light. So this is the Compton effect. So this also cannot be explained in terms of wave theory, but still we are using here wave nature because we have studied this in 1923, and already Planck and Einstein has used this theory that wave and particle aspects can be interrelated or it can be used in same situation. So Compton has used particle nature, so we can explain this Compton effect using particle nature. We don't actually need to have this wave. As I told in photoelectric effect also, we can just say that photon of some energy and here photon of another energy, because energy is reduced. We can say here the energy of the photon is E dash and here it is E. So we don't even need to say that there is some wavelength, but what we observed, because we can measure wavelength or frequency of light, we observed this. And why this happened, was explained using particle nature. So similar to the collision, we can say collision is the case. So there is some particle is colliding with another particle. This particle gets energy, and first particle reduces its energy and rebounds. So that was the case. So similar case was the Compton effect. That's why this can be explained using particle nature, and wave nature is used here, but it is not required, just like photoelectric effect. So this was the we have not studied Compton effect earlier, so we have covered this. So these all effects contributed. We will also see the Raman effect in some next videos. So all these concepts were gave birth to wave particle duality and supported wave particle duality.